Let's talk about dielectrics. I have a parallel plate capacitor here. Here's the left plate, here's the right plate, here are the wires, and this is the dielectric. And I want to go over how the dielectric affects the behavior of the capacitor. So, remember that we have electrons coming down the wires, and that first electron will come and be deposited onto the plate. And because of Coulomb's law, it's going to repel an electron off the other plate. And since that electron is left, that means this side becomes positively charged. And you just add more charges and fill up the plate. So I'll do that right now. And you end up with an electric field. The electric field goes from positive to negative. So you end up with an electric field that's between the plates that's going this direction. So that's the electric field between the plates. Now the dielectric itself is made up of atoms. And atoms, as you know, are made up of protons, electrons, and neutrons. And although the atom itself may be neutral, because it has positive and negative charges, they're going to respond to the electric field, to any electric field, but in this case, the electric field created by the plates. And so that's going to cause the atoms to become polarized. That is, here the protons and the electrons are going to react. So the protons here where I've drawn, they're attracted to the negative plate, whereas the electrons are repelled. But of course, they're still bound, and so the atom has essentially reoriented itself and become polarized. And that happens all along this left side, like so. But it also happens on the right side of the plate. Here, the electrons are attracted to the positive plate and repelled. The positive charges, the protons, are repelled by the positive plate. And so you get this. Oops. And to some degree, this happens throughout the dielectric. How much it happens depends on the dielectric itself, what it's made of. But this results in the left side of the dielectric being positively charged and the right side being negatively charged. And so you get an electric field created by the dielectric. It's going to the right. Okay, now let's look at our formulas. We know that capacitance is Q over V. And we also know that for plates, for parallel plates, V is going to equal ED. And so we can combine those. And we get this. But it's important to realize that this E here, this E is the net electric field. And the net electric field is going to be the E of the plates plus electric field of the dielectric. Now, if there's no dielectric, then it's just E of the plates. But if you do have a dielectric, you've got to take it into account as well. And you can see that these two electric fields are anti-parallel. And so when you add them together, that's going to reduce, it's going to make the overall electric field less than it would be if there was no dielectric. So the magnitude is decreasing. Over here, the magnitude of the E field is less than it would be without the dielectric. And so that means for a given amount of charge, the capacitance is higher. So putting a dielectric in increases the capacitance. And you can see that from our formula for the capacitance for a parallel plate. You have the dielectric constant times epsilon naught times A over D. So for a vacuum, K is 1. K is 1. And K, remember, has to be greater than or equal to 1. And so for anything else other than a vacuum, it's going to be greater than 1, and that's obviously going to increase the capacitance. Now, I want to talk about how this all affects the energy stored in the capacitor. And so I want to look at a couple of examples. Let me go down here now. So here I've got my capacitor. Notice I haven't put the dielectric in it. So I'm going to charge up my capacitor. Let's do that real quick. Negative, 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 negative. Okay, so now my capacitor is all charged up. Now, let's assume it's all connected to a battery. Let's assume I disconnect it. It's no longer connected to the battery. Now, I can state the energy here. Potential energy is 1/2 QV. I can also say it's 1/2 CV squared. We can also say it's Q squared over 2C. Okay, so I've charged it up. I don't have the dielectric in there. I've got some amount of potential energy, and then I disconnect it from the battery. Now, I'm going to put the dielectric in there. So now I move the dielectric in. And the question is, okay, what's going to happen to the capacitor? What's going to happen to the potential energy? Well, realize the charge has nowhere to go. The charge has nowhere to go, and so consequently, in this situation, Q is not changing. What's changing? C is changing. And because C is specifically, it's increasing, and so I have just decreased the amount of potential energy in my capacitor as a result of that. Now, let's look at a different situation, though. Let's say instead of disconnecting it from the battery, I left it connected to the battery. Okay. So now when I put that dielectric in, now the charges have somewhere to go. What has to stay constant in that case is the voltage. It's connected to the battery. That's a constant voltage source. So now the voltage stays constant. Well, if the voltage stays constant, now V is staying constant. C has just increased because I put in the dielectric, so I've suddenly increased the potential energy between the plates. In general, you're going to be charging something up to a certain voltage. So by putting a dielectric in general, you are going to increase the potential energy of your capacitor. But there are situations, as I just went over, where you will actually decrease the potential energy, and that's because you're reducing the electric field. And those situations are that first example where the charge didn't have anywhere to go because it was disconnected, and so consequently the charge stayed constant. This stayed constant, the capacitance increased, and that decreased the potential energy.